This is the last talk for today. So we have Debjyoti Biswas talking about algebraic construction of optimal recovery for arbitrary quantum noise channels.
Yes. Yeah, thanks for the introductions, and thanks for giving me the opportunity to thanks for giving me the opportunity to present our recent work on constructions of the optimal error corrections protocol for any arbitrary quantum channels. So this was quite motivated by lectures on 2007 on quantum error corrections conference, the first meeting by my supervisor Ramanujan, and the framework that I am going to present here, the algebraic way to construct algebraic way that will help us in constructing the optimal recovery. But the thing is that there exists a framework for constructing the optimal recovery, but the thing is that framework is an NP-hard problem because it consists of numerical search based on the semi-definite programmings, and if you increase the length of your encodings or the system size, it is getting hard. So let's start with the descriptions of the noise. What is a noise? Because noise is something that it appears big because of the system and environment interactions and its losses of the coherence, and this thing can be mapped. The noise process can be modeled as a completely positive and a trace preserving map, which we can evaluate from a joint unitary evolutions which is acting on the environment and the system. And if we trace the environmental degrees of freedom out, and then we will have a nice representations called the operator sum representations, and these operators are known as the Krauss operators. For example, if I consider one of the dominating noise process in various physical realizations of the qubits is the amplitude damping noise, and it can be modeled with a two Krauss operator where this gamma represents the probability of damping or probability of jumping the or decay. So with this probability, the system decays from ket 1 to ket 0, from the excited state to the ground state. So the next part obviously is the how to protect a system from noise. So quantum error corrections gives us a framework which tells you that if I encode my informations in a smaller subspace of a Hilbert space, and this code can correct a set of errors only if those errors map this code space to an orthogonal subspaces. And if it is orthogonal, then I can detect these subspaces, and then accordingly I can apply a recovery. So these detections is known as the syndrome extractions or the syndrome detections, and the whole procedures from here, from the syndrome detections and the recoveries, this feedback can be modeled with a recovery operator which is characterized by these operators. P is the projected onto the code space, and UIs are the unitary operator that comes out from the polar decompositions of this operator AI followed by P. So a code and a noise process which satisfies these conditions, which we call the Nil-Laflamme conditions, guarantees that there exists a recovery something like this. But we are interested in a slightly different pictures where we have a code, but my noise process maps my code space to a set of subspaces which are not orthogonal to each other, which are overlapping with each others, and it gets deformed because of the noise. So these pictures can be captured in these conditions. You can see that because of this part, which is a perturbations on the Nil-Laflamme conditions, this part tells you that these subspaces will be overlapping if it is non-zero, and it also tells you that because of this error, it rotates my say for the qubit case, it rotates my logical 0 and the logical 1 by different amounts. So that's why it is the deformations comes. Now the thing is that for these kinds of pictures, we can have a recovery, or after the recovery, if I measure the closeness between the recovered state and the encoded state, it should be something like 1 minus of the order of epsilon to the power t plus 1, only if my deformations or my perturbations on the nilaflams is small. It scales as epsilon to the power t plus 1, where this epsilon is nothing but the noise strength. But the thing is that, like here we have, if some code and noise satisfies these conditions, I can guarantee that this is my recovery. But what sort of recovery should we have here? So for example, if I consider this 4-qubit code, which is a noise adapted code, it can correct only the amplitude damping noise process. It has a stabilizer generator like this. But as you can see that, if I want to detect the syndromes, I have a degeneracy in the syndrome tables. Say these first two syndromes are degenerate since they are similar. So I cannot distinguish which qubit face the damping. So for that I have to measure a separate set of operator. Note that these are not so these are not these sets of operator doesn't commutes with these sets, so that can hamper my code space. But this operator stabilizes the noisy subspaces or the syndrome subspaces. So after measuring all these 4 operator, I can tell which qubits got face the damping. But but again the question is that what should be the feedback, or what should be the recovery, or how should I correct this noise? So answering that, so the problem is with these kinds of pictures is that we have an overlapping subspaces. So what we have proposed, since we have an overlapping subspaces, we can follow a Gram-Schmidt type orthogonalizations of the subspaces itself. The algorithm starts something like given these noise channels AKs, which satisfies the nilaflam conditions perturbatively, I am interested to construct a separate noise channels which has these Krauss operators, which doesn't have these kinds of perturbations. It has some sort of deformations on the code space, but the orthogonality is guaranteed. So how to construct this? So let's start with the choice E1 be the first element of my set to be the A1. A1 may be the no damping noise or maybe the zero noise operators. And then I construct the second operator of the set by these procedures, where this U1 are nothing but the polar decomposition unitary comes out of the polar decompositions of E1P, and this P1 is nothing but the projector onto the non-null space of this operator. And you can verify that this thing is zero. So that tells you the subspace, the code space got mapped by these E1 operators is orthogonal to the image of this operator. So we can detect those subspaces. So we can generate a kth operator of this set like this by following the same procedures, and we can verify that this UI satisfies, sorry, here should be J. So UI dagger Uj is delta Ij. So that guarantees that different syndrome subspaces are orthogonal. And this also implies that my new channel is trace non-increasing, which makes it physical. So again, what is the recovery? So the aim is that I started with these pictures where my subspaces are overlapping. After the algorithm, I have ended up into these pictures where my subspaces are non-overlapping, and my new set of Krauss operator satisfies these conditions, but the deformations is still there. But we can construct a recovery just like the perfect recovery. Perfect recovery means if I go back to this slide, just something like this. But the thing is that this recovery is not an optimal recovery. So the question is that right now is we are reverting this subspace back to the code space, but actually in error corrections what we do, we revert these subspaces back to the code space. So what guarantees that this recovery should give me a good fidelity, or using this operator we can perform a quantum error corrections. So to answer that, we measures the overlap between the newly constructed subspaces and the older subspaces that gives me the measures on how close these two channels are on the support of the code space. So actually we are going to bound these operators. So from the Schwarz inequality we can see that this is an upper bounded by this, but note that these vectors are linearly dependent. So this inequality becomes equality, and this closeness is exactly equal to this. So when I calculate the fidelity, it will get reflected, and we can show that the fidelity is lower bounded by these operators. But we have taken a different route to correct the noise. So the first thing is that I can characterize my error corrections protocol by measures of the worst case fidelity, which is the minimizations over the state on the code space, and this is my fidelity measure. So if I vary the channel, you can see that the value of this fidelity mean square will vary. So if I choose if I find an optimal recovery, I can get a best value of this. But finding an optimal recovery is a hard problem, because executing SDP for a larger code is numerically hard. But we can construct an near optimal recovery, which is an universal recovery also, which is called the PETS map, which has a nice Krauss operator decompositions, and these EIs are nothing but the noise operators. Note that for a perfect code, this is exactly similar to the perfect recoveries. And some recent work by the group of by Liang's group shows that with regards to the entanglement fidelity, this map can serve as an optimal recovery only if this equality holds, where M is nothing but this operator. This operator is the M. So we take an example for whether this thing can give me a optimal recovery for any general kinds of noise process and generic codes or not. So we started with this thing, and we end up with the orthogonalizations, and we ask that after the PETS recovery, how close the recovered state and the initial states are. So the actual PETS map, which is adapted to the actual noise process A, looks like this. But we are going to adapt the PETS map to our constructed channels, which we got from the orthogonalizations, which has the Krauss operator something like this. Now, let us take the example of the amplitude damping noise and with the 4-1 code. But now we see that these operators are diagonals onto the code space, and if I calculate the entanglement fidelity for the 4-1 codes and with the PETS recovery, which we have adapted to the newly constructed channel, we see that the entanglement fidelity is exactly 1 minus 1.25 gamma square, where gamma is the damping probabilities, and it is exactly similar to the recovery that the fidelity that we obtain for the optimal recovery from the semi-definite programming, which was first reported by Fletchers and Peter Shore. So we also look at whether there is any differences between the optimal recovery that we obtain from the SDP and the optimal recovery that our PETS map gives us. So the thing is that you can see that each and every operator R0, R2, R3 to R9s are exactly similar, but these R1 are not the similar. The difference is that here, instead of the 0 in my PETS recovery, I have Ket1L, which is the logical 1 operator. So that is a small difference that we have here. And in summary, we have proposed a framework to perform an approximate quantum error corrections despite of having the overlapping syndrome subspaces, and we show that this PETS recovery can serve as an optimal recovery for some codes, but in futures we want to show whether this can be done for, or we want to show analytically that it actually serves as an optimal recovery for a generic codes. And we know that how to implement a CPTP map, since it is a CPTP map, how to implement a CPTP map on a circuit and how to simulate it on a hardware. But whether we can implement this PETS recovery, which is adapted to the modified channel with a lesser resources and fewer circuit depths on the hardware efficiently. Yeah, thank you.
So thank you. I wonder whether this can be carried to more ambitious settings. And I'm thinking about, say, superconducting qubits, where many interesting experiments are done now. And if as you've said, the dominant or an important contribution to the noise model is the amplitude damping. Yeah. But there is significant Z noise as well. So the model would need to be extended. And I wonder if you took, even you or someone, your successor, took the existing situation where people don't use the amplitude damping codes, but just regular full ordinary distance codes like the surface 17, that kind of thing. And whether the strategies you've just discussed would lead to different or useful decoding methods, also in the face of the fact that the decoding is noisy. So that's another aspect that's different from your setting.
Yeah, we can. We had a plan for a more generic kinds of noise with the amplitude damping. If I had the phase damping as well. So the plan was there exists also a PETS recovery for a subsystem code. So
I would say just Pauli Z would be adequate.
Yeah, Pauli Z.
Additional
yeah. Noise. So the aim was that if I can have a DFS or the noiseless subsystem for the Pauli Z, or if I with the dynamical decouplings as well, if I can mitigate the Pauli Z up to some extent.
So your ambition was to make up a new code rather than just see how existing codes would perform.
So with this 4.1 code, if I want to run the PET circuit on the actual hardware, so if I apply the dynamical decoupling, some optimal dynamical decouplings, that can mitigate my phase damping to some extent, and then we end up with only the T1 noises, then whether this is good protocol or not, because we have to think about the circuit depths as well. It cannot be too much.
Okay, thanks.
Any other questions? I have a trivial question. Maybe how difficult is the scalability to more than 4 qubit? You said that.
We had work on this. It implements the PETS map. So for a generic code, it scales exponentially. But here, that what our assumption is that for a generic codes, we can still, if we can perform some syndrome extractions, and depending on the syndromes, if we can implement some unitary operations, which will model this adapted bits map to the modified channel, that can be much lesser. Say for example, right now what I have the circuit for the 4.1 code with this modified channel, we have 26 CNOTs all total. So maybe I don't know for the what it will happen for the 513 codes or the 9 qubit short codes. Yeah. Yeah.
Thank you. So this brings the end to the session. So thank you for attending.